Hi everyone, in this video we will study how to efficiently implement Prim's algorithm. Now in the previous video in this playlist, we studied Prim's algorithm and worked out an example. Now Prim's algorithm, as you will recall, is used to find the minimum spanning tree in a graph. So let's recall the idea of Prim's algorithm. What the algorithm does is, it first selects a vertex in the graph. And this vertex is stored in the set S. A is initially empty. So S would contain all the vertices in this tree, which finally would be all the vertices in this graph. And A would be the set of edges from the graph which are part of this tree. So we start off with some random vertex of the graph, that is R. That is going to be the root of this tree. Then we are going to find the lightest edge such that one endpoint of this edge lies in S and the other endpoint lies in V minus S. So it's the edge that grows from the set S to the set V minus S. Now you're going to add this set to A. And then you're going to take the other endpoint, basically the other vertex which is currently in the set V minus S, and add that to S. And you're going to keep repeating this process until unless the set V minus S goes to null. That is, basically you've added all the vertices in the graph into this set S. In that case, you've actually spanned all the vertices of this graph. So now the questions that would arise is, why does this produce a minimum spanning tree? And how to efficiently implement this algorithm and find the lightest edge? And how do you update A efficiently? And how do you update S efficiently? So these are the questions that would naturally arise. Now what we are going to do is we're going to answer the questions in the opposite order. First we will study how the algorithm updates S efficiently. Then we will find out how does the algorithm find the lightest edge and update A efficiently. And once we do these two, you would know how to find the minimum spanning tree. As you would have seen, I've split the screen into two halves, on the left and on the right. On the left, we'll go through the slides, and on the right, we'll basically work out an example on this particular graph. So first, let's try to find out how the algorithm updates S efficiently. To update S efficiently in the implementation, what we assume is each vertex has a color. So initially, all vertices are colored white. Whenever a vertex is moved to the set S, it is colored black. Now, we would use this array V, color V basically, to store the color of a particular vertex V. Now, the next question is, how does the algorithm find the lightest edge and update A efficiently? The answer to this question is, we would use a priority queue to find the lightest edge. And then we will use pred V to update A. So we will see how these are used in Prim's algorithm. Before that, let's just review priority queues. Now, priority queue is a data structure which supports the following operations. And one of the easiest way to implement priority queues is to use a heap. Now, the priority queue supports the operation insert. So insert U, comma key says that you have to insert U with the key value key in the priority queue. So Q is the priority queue, and you're inserting U, and the key value of that is key. Now, extract min will give us the item with the minimum key in the queue, capital Q. Okay, so that is what extract min is going to give us. And extract min is going to be very useful for us. Now, decrease key will decrease the value of U to the new key value. Okay, so you can decrease the value of the queue. Now, priority queue can be implemented very, very efficiently, and each operation only takes O of log cardinality of Q. That is the size of the queue. Okay, so you can do every operation in log of the size of the queue. And to know this, you can actually look at CLRS, the Codman's book. Okay, so how do we use the priority queue to find the lightest edge? Let's first understand this, and then we will go to the pseudocode of Prim's algorithm. Now, each item in this queue is denoted by a triple. U basically the item itself, then U has pred U, and then there is key U. Okay, so U is basically the vertex, is a vertex in V minus S, which has currently not been added to S. So U will be one item, which is in V, vertex in V minus S. Now, key U, and this is very important, is the weight of the lightest edge from U to any vertex in S. So S is the set of vertices that have already been explored and have been added to the tree. So U is a vertex that lies in V minus S. Now U can be connected to a bunch of vertices in S. Now key U is the weight of the lightest edge from U to one of these vertices in S. Now pred U is the end point of this edge in S. Okay, so let's try to understand this with this example that's given here. So all the nodes that have been marked dark black are already in the set S, and all the vertices which are marked white are in the set V minus S. So let's first look at all the keys for all the white vertices. So key of F is 8. Okay, this is because F has two edges which go into the set S, FE and FC, and FE has a value of 8, while FC has a value of 14. So key of F is 8. Pred E is pred F is actually E, because that is the other side of this edge. Similarly, key I is going to be infinity, because I is not connected directly to any of the vertices in S, and pred I is therefore nil. Key of G is going to be 16. From G, there are edges to C, A, and B, and GC has a value of 16, while GA and GB have a value greater than 16. So key G is 16. I just want to note that I cannot write on this side, on the left side of the screen, and I can only write on the right side of the screen because of the iPad, and that's where I am going to work out the example. So key H, coming back, has a value of 24 because H is directly connected only to B, and that has a value of 24, and pred H is B. Now, among these different nodes that are, or vertices that are in V minus S, key F is least. So F has the minimum key. So what you're going to do is, the algorithm, what it's going to do is, it's going to add FE to A and F to S. So that is the lightest edge that goes from the set V minus S to S. So you're going to pick that lightest edge and add it to A. Okay, that is the idea of finding the lightest edge. You look at all the keys, and then whichever key is the least, that is the lightest edge. You just pick that, and by looking at the pred, you know which node it is connected to in S, and basically that gives you the edge and pulls over the other vertex to S as well. So you can, if you look at the right of the slide, you would see that the new edge FE is now added. Having understood this, now let's go to Prim's algorithm. Okay, so in Prim's algorithm, what we're going to do is, we're going to first, every vertex initially is going to be white. Okay. So all the color of all the vertices are white, and the key of each vertex is going to be infinity. And I'm just going to write this here. So key of each vertex initially is going to be infinity. And pred is initially going to be nil. Just assume that, and let us assume that you're going to first choose A in this particular example, in this graph, as the root node. Okay, that's where we're going to start off with. Now, if you go to this algorithm, it says that key of R is going to be first assigned to 0 after the initialization. In the initialization step, I just assigned all the preds to nil as well. That does not matter, though it's not done explicitly in this code. Now, pred of R is also initialized to nil. Now, what are we going to do? You're going to put all the vertices in Q. So all these vertices in V are going to be added to this priority queue, Q. Now you're going to iterate through this priority queue while it is not empty. So while Q is not empty, will help iterate through the entire priority queue. Now in the next line, it says Q U equals Q of extract min. So extract min is going to extract the lightest edge. That is the goal of the extract min function. Is going to extract the lightest edge. Okay, so and then what you're going to do is, or what the algorithm is going to do is, for each and every vertex which is adjacent to you, which has been picked by this extract min, this is what we are going to do. We have the inner loop, okay, where you have this condition for each V adjacent to U. You're going to check if V's color is W. That is, it has already not been explored and it has already not been added to this to the set A. And then you're going to see if the weight is less than of that edge between U and V is less than the key. If that is the case, you're going to actually decrease the key. Okay, and then you are going to change the color to black, of U to black. Of course, by just going through this entire description, it's just very hard for us to understand how the algorithm is working. So we will look at this example. Okay, so now we are going to pick A as our root. Okay, so if A is picked as root, then key of A is going to become 0 and pred R is already nil. So here it's going to become 0. Okay, now we are going to add all these to the priority queue, and then the while loop is going to start. So U equals Q dot extract min. If you remember what the extract min does, if I go back, the extract min is going to extract the item with the minimum key value in the queue. So here it is going to extract A in this case, or the root R. Okay, so that is what U is going to contain in this step. So U equal to Q dot extract min is going to give us initially A. Now we are going to look at all the neighbors of A. That is, for each V adjacent to U, we are going to look at all the neighbors. So in this case, we are going to look at B, D, and E because they are directly connected to A. Now, initially, all of these are going to have color white. Now, all of their keys are infinity. Okay, so W, U, comma V is obviously less than key. Therefore, we are going to update the values of their keys. Okay, so let's first update the values of the keys, and then we are going to also update the pred V. Okay, so pred V here you're going to assign U to pred V. So basically, pred V is going to be A. So let's go ahead and do that for B here. So I'm going to erase these B, D, and E. I'm going to erase these. Okay, so B is now going to have the key of B is going to be 1, and the key of and its pred is going to be A. The key of D is going to be 10, pred is going to be A, and D of E is going to be 3, and pred is going to be A. These values, for example, why is the key of D 10? Because AD has a value of 10. And that initially the key was infinity, and we just compared 10 with infinity, and we put it there. After this process, you will come out of the for loop and will color U to black. Our U is actually A, so A will be colored to black. So I'm just going to color this as black. Okay. So that's our A. That's been colored to black. Now we go once again. Now, because the Q is not empty, you're going to extract U equal to Q dot extract min. B is the one value which is the min here. So that will be at the head of the Q. Basically, you will extract the B. So U will be B in this next step. Now, we're going to look at all the neighbors of B. So B is directly connected to B is connected to A, it's directly connected to D and C. Okay, those are the three edges we're going to look at. Now, color of A is black. So that's already been added. So you're not going to consider that at all. Okay, so you're going to consider the vertices D and C. Now, for D, the key B of the W of UV, that is going to be 3. Okay, that is less than the key that is stored at D, which is 10. So you're going to compare W of BD less than key. This is what we are comparing. W of BD is 3 and key of D is 10. So we are going to update that key. Okay, so let's go ahead and update this. So this is now going to be 3, and here we are going to update B. Okay, at this point we will next go on to the next vertex that is connected to B, which happens to be C. C currently has a key value of infinity, so we're going to update that. The value that it's going to be updated with is 2, and pred is going to be B. Okay. After this, it's going to come out of the for loop, and you're going to color B to be black. Okay. So now let's go to the next iteration of this algorithm. I hope you've already started understanding how the algorithm works. So now you're going to look at the other vertices which have already not been colored. So currently what it would do is you're going to extract the min. Okay. Now what is going to happen is A and B have already been extracted. So I'm just going to put a tick on these two. So they are not part of the queue anymore. So C has a value of 2. Okay, a key value of 2. So it's going to come out. So U is now going to be C. Now we are going to look at the neighbors of C. So let's raise these. So the neighbors of C are B, D, and F. B has a color of black, so we are not going to go inside the if statement. D has a color of white, but its key, but W of CD will compare whether it's less than the key at D. W of CD is actually 4, whereas the key that's stored is 3. So this condition fails. Key of D is 3. Therefore, it's not going to go into that if statement. For F, CF is 5, whereas the current key value at F is infinity. So we're going to update that. So this is going to be 5, and pred U is going to be C. After this, you're going to color C to be black. Okay. And that's why I'm going to put this tick over here, because that is no longer part of that. Okay, so now let's look at the next node. We can pick D or E because both have the minimum key. Let's just pick D. Okay, so U is now going to pick BD. Erase all this. So U is now going to be D. Now let's look at all the neighbor. So every vertex in the graph is actually a neighbor of D, but A, B, and C have already been explored, or they're already black in color. So we're only going to look at E and F. So DE has a weight of 4. So W of D comma E is 4, and the current value stored at key E is actually 3. So it's not going to go into that if statement. Okay. Now let's consider F. So WDF, that is 1. And the key that's stored at F is 5. Therefore, it is going to go inside the if statement. And then what we're going to do is we're going to update the key of F. Key of F will now be 1, and its predecessor is going to be D. After this, we're going to color D to be black. Next, we are going to take the next vertex which is left in the queue, which is E and F. F has the minimum value, so now U is going to be F. So U is going to be now F because it has a key value of 1. So we pick F, and F is not connected. So its F is directly connected to C and D, but they are both are black nodes. Therefore, it's not going to go into the if statement. So come out of this, and you will plaint F to be black. Next, you would extract E, and essentially you cannot update anything because all the other vertices are already black. So that is the end of the algorithm. Okay. So we just took E as well. So now you're going to return everything. Okay. So basically A is going to be your root, A and nil. So that's what you're going to return. The next is going to be B comma A. Then you are going to return C comma B. And then there is D comma B, E comma A, and F comma D. Using this, we'll actually construct our spanning tree. So let's just pick the color red. So here this BA. Okay. So we took this already. CB is this one here. DB is actually this one here. EA is this one, and FD is this one. So this is the minimum spanning tree for this particular graph. So in this way, using adjacency, using the priority queue, we can actually efficiently implement the minimum spanning tree. So use priority queues as well as coloring. Now, before I end, I would just like to talk about the running time a little bit. So there are n vertices. v vertices in this in the graph, and there are e edges. Now you take O of log n to extract each vertex from the queue if you implement it efficiently using heaps. So O of log n is what you will need to extract each vertex from the queue. Now there are n vertices because n is v basically here. So for all the vertices you will take O of n log n. Similarly, to decrease the value of a neighbor, you take log n time. Therefore, as it's done at most once for each edge, you will take O of e log n. Therefore, the total cost of running Prim's algorithm is O of n plus e log n. Or if you want to write it in terms of v and e, it's going to be mod v plus mod e times log of mod v. So with this, I'll conclude this video. In this video, we talked about how to efficiently implement Prim's algorithm. Thank you for watching.